Buenos días a todos. Gracias por venir a nuestro taller. Él es José Ignacio.
Good morning. This is José Ignacio Escribano. I'm Alfonso Muñoz, and we're going to talk to you a little bit about AI, which seems an important subject for everybody, but related to computer security. We're talking about offensive and defensive security with machine learning. That's the title of our talk. But as you'll see, we're going to be talking offensive security because we're seeing that many attacks are arriving. We'll look and see whether we can be defended from them. Let's a little bit of information about who we are. I'm Alfonso, and you can see the other person with me is José Ignacio. So there are contact details. If you need to contact us, you can contact us by email or on our Twitter accounts. What's our aim today? Well, we're going to show you. We've got a GitHub published if you want to replicate anything that we've done. What we want to do is to remove all the worries, the concerns, the mist that surrounds this subject. We'll look at the different issues, theoretical and practical, and we're going to spend some time especially talking about offensive. We'll talk about all the different attacks on artificial intelligence systems. Some are practical. They're tools that can be downloaded and can be plugged in, and others that are still theoretical, but just go to show what can be done. So we're going to do the following. Firstly, we're going to give you an overview of the context of artificial intelligence. So if somebody's new to this world and knows nothing about artificial intelligence, just a brief context setting. We'll talk about what makes AI unique. We'll then have José giving you a little more practical approach. We're talking about machine learning. We'll give some demos. We'll see how neuronal networks work. And we'll also talk about hacks, adversary networks as well. So once we've done this context, we'll then move on to security. We'll talk about the limitations and context to security, and we'll give you a brief overview of what's being done in defensive security. And with those limitations and context, we'll move on to what's less spoken about, which is offensive security. We'll talk about all different black box, white box attacks, and something that's also very important for us, which is how to make AI be safe from a computer safety viewpoint. We'll then draw some conclusions. So the context. As you probably know, artificial intelligence is, and machine learning, it is part of artificial intelligence. What it allows you to do is, via software, allow machines to learn independently. And to a certain extent, we're trying to imitate the reasoning of human behavior, but automatically. And in fact, this kind of technology is so important, and I don't know if you've seen this table, it's quite a famous companies in many sectors are trying to use this technology to get some kind of competitive edge in all sorts of industries, agriculture, education, investments, legal areas, and logistics. And we're just going to concentrate on this area, which is how to apply AI to cybersecurity. And I say it's virtually anecdotal because the control we have it is very limited, because there are many things that mean that in our field it's very difficult to apply this. So if you look at this table, there's a lot of information about tools, environments, etc. If you know and you've worked with these technologies, this is a very good summary of how they work. What is AI and why is everybody so excited about this technology? Well, we think this slide summarizes it quite clearly. There's a whole series of apps that actually profit from the possibility of automating certain human behavior with certain different techniques that are already known. There are many scenarios where this is successful. So we've got the classics, fraud detection, image classification, recommendation systems, a whole series of scenarios where these kinds of technologies are very useful. And something that we're very concerned about from the view of computer security is to what extent AI is a technology that can be controlled. Is it controllable? There are many experts who fear this idea that AI could develop such ability that a human being isn't able to control it. In the press, you may have seen people are trying to reach common standards to control this kind of intelligence. If you've got time, when these slides are published with this article, have a look at them because they show many of the mistakes of AI in recent decades and how cybersecurity has failed and how things can go badly wrong if we don't do things properly. Here, we've given you the typical opinions that many scientists written about machine learning. They try to bring together information about this subject. And another problem that many people are concerned about is its impact of the impact of AI on the economy and society. And in fact, if you've read, some people are talking about charging robots taxes and whether robots are going to take our work away from us. But what we're worried about is not just the economic side of things, but the societal side of things. Whether these areas may bring out the worst in human beings. They may end up making us more racist, because it's been shown that terrible things may happen. For example, bots that identify people by race and that encourage them to be racist. So what we're saying is that we need to be very careful with the technology. And at the end of the day, what it's summarizing is the following. Because AI is what's called a singularity. So that's the time when this kind of AI can solve a problem as efficiently as a human being. When is this going to happen? Well, it depends on many things. The problem that we have is, as human beings, that we're very bad at predicting the future. We virtually always get things wrong. In fact, nobody knows when this is really going to happen. The only thing that we can refer to is some surveys carried out by the Future of Humanity Institute. And here what they've said is that between now and 40 years hence, many activities that humans do today will be done by AI at least equally as well as humans. And they've given, for example, a 20-year time span for more or less the time when the majority of tasks that humans carried out will be able to be carried out by AI, by robots. We're talking about surgery, we're talking about all sorts of things. So this is the uncertain scenario that we find ourselves in, and what makes people so concerned about these kinds of technologies. What we don't know is when these kind of algorithms are going to be able to replace the ability of a senior analyst, for example, with testing, reversing, etc. So, our specific opinion on this is that if you've got a good security analyst, normally AI isn't going to be able to replace that person, but what AI has is it can be replicated. For example, I may have a person that's very good at doing reversing, but I don't have 5 people or 10 people or 100 people that could 24 hours a day repeat that. So what's good about AI is its scalability. It may not be as good as human beings, but as long as they're reasonably good, they're going to be able to replace many tasks that we do. As I said earlier, the main problem is that people don't really know where this road is heading. In fact, the owners of major organizations such as Tesla and Facebook are continually debating whether this is going to have an impact or not and what its reach will be. And there's a great deal of uncertainty once again. Let's now quickly look with a couple of overheads of justice or fairness, i.e. to what extent AI is so powerful and whether it will affect security. Here, we've given you a series of examples, especially from video games, which is the typical one that people are always struck by, to see how this progress has developed. And here you can see how in, I think, the most recent 20 years, AI has made very slow progress. It's dealt with certain specific problems. Some of them it's resolved very well, but it can't be used as generally as human intelligence. So if you look at artificial intelligence, you can see it actually really dates from the 1950s, but it's over the last 20 years that things have been done, but not perhaps as quickly as many people might think. In fact, this is a typical example that people are always struck by. These are different simulations that we've made of AI playing video games. And you can prove that for many video games, AI plays better than a human being. So you can have algorithms made that actually play better than a human. So for many scenarios, maybe for security, these are interesting. We're not worried about these games because it's just an anecdote, but what people begin to get worried about is the ability to play games and develop AI algorithms that actually reflect human intelligence. And an example of this, or a disruptive point, was with the different bets that are made to beat, for example, AlphaGo Zero. So today, things are evolving far more rapidly. We can do very good specific algorithms, we can develop them, and we get the results that we all know about with them. I like this study carried out by Google, especially. I don't know if you've seen it. What Google did was an experiment with neuronal networks. In blue and red, you've got two neuronal networks that are competing. They represent apples. What happens is the neuronal networks, as there are lots of apples, they collaborate. That is, they decide to collaborate if there are lots of apples, but when there are few apples, they decide they have to compete, so they attack each other. These red dots represent lasers, but there's another scenario. That is, if you're faced with different neuronal networks, one has greater computational ability than the other, so therefore it can train rapidly than the other one. It doesn't matter how many apples there are, they'll always attack, they'll never collaborate. And that is deduced by the network. And that's what many people are concerned about, to what extent AI can be controlled. And from a security viewpoint, it's, okay, if I use this kind of method for defensive security, is it going to turn on me? That's what we want to know. And here, I'm going to give you a couple of references to articles talking about these subjects. I actually recommend you watch this video, a video published by CECIC. There's also an article about how Google has got things wrong, an article that I mentioned earlier. AI is useful at the end of the day, but we need to remember in what context, in what domain it should be applied or not. And finishing this section about context, and I'll move on to the more technical side of things, there are some aspects which some people think about, forget, which for us in the security world is very important, which is everything related to legislation. There are scenarios where even if we had AI algorithms that were better than human behavior, they cannot be used because legislation is going to prevent us from doing from. Let's imagine a bank that has to give a loan. The data protection law may force that those decisions that impact a person's normal daily life have to be reviewed, especially if they impact, for example, a URL. And that's because you can have a black box made, you can have inputs but not outputs, and you don't know why inputs don't lead to outputs because there's no reasoning. So there are many scenarios in which this technology cannot be used. If we want the best security system, it may well be that we can't actually use it because of legal problems. Having given you context, let's now move on to the technical side of things. Let's talk about machine learning. Machine learning are basically data and algorithms. You have some data, an algorithm is applied to the data, and we obtain a model that allows us to carry out different tasks. The data can be in any kind. Here they're represented as binary data, but they can be text, images, audio recordings, whatever we want. That takes us onto algorithms. We can classify the algorithms depending upon the type of learning and the task that they solve. Let's look at learning first. There are different types. There's supervised, non-supervised, and backup learning. The supervised learning, what it tries to do is to learn a task through tagged data. If we want to identify, for example, pictures of dogs and cats, in each picture we add a tag to say whether it's a dog or a cat. So what this function does is it learns from these tags, unlike non-supervised learning where those tags don't exist. And the aim of this kind of learning is to obtain the internal structure of the data. And finally, backup learning, which is different to the other two. And in this case, we've got a robot in a certain environment, and this agent or robot knows the state and carries out different actions. For every action that it carries out in a state, it receives a reward. And the idea of this agent is to maximize the reward. We can also classify things according to the task that's solved. Machine learning can be applied to different kinds of applications, but it can be grouped into 4 different types, which are called tasks: classification, regression, clustering, and dimensionality reduction. Classification and regression are part of supervised learning, and the other 2 are non-supervised learning. So what happens here? You have a series of predefined objects or classes, like the cats and dogs, as we said previously. And the idea is to differentiate between these 2 classes, between the cats and the dogs. Regression, in this case, we don't have a finite group of classes, but rather an infinite interval. So we try to approach a function to these data. Clustering involves grouping together objects depending upon their properties. To give a typical example, we've got market segmentation. For example, if we've got 1 million customers, we want to offer these customers a tailor-made tariff for each one. That's impossible. So we segment the market into 4 or 5 user groups, and each user group is offered a certain tariff, a certain rate. And then dimensionality reduction. Normally, we have data with some variables. If there's lots of data, some may be redundant. And in the case of machine learning training, this can take its time, because if you reduce all these variables, you can lose information. But this is a way of making training more efficient. Each type has several algorithms. So what we've done is search in Kaggle for a page where different machine learning competitions are carried out. And here they've carried out a survey where many questions are asked. Here there are just 2. The first question is, what data science methods are used at work for those that use Kaggle, and what tools are used at work? And if we look, the ones that are most used are up there on the screen. You've got logistic regression, decision trees, random forest, neural networks. And as for programming languages, the one that's most used is Python, followed by R, which is used by mathematicians and statisticians. Then we've got others, such as Jupyter Notebooks or e-learning frames. The problem of machine learning isn't so much algorithms, but where they get their data from. Either because we need to apply, or we want to make an application for something, but we don't have the data because the data aren't published, or because they're very bad, they're dirty data. So there are a series of data repositories where you can see the kinds of data. Each data type has different categories. Maybe the most interesting one is the Kaggle data sets, because they do all kinds of competitions on all kinds of themes. Also, the data from the web service from the US and from Amazon is also interesting. And also Secrepo has also have several security data sets. One of the data kinds most used in security or machine learning in general are pictures, images. And here you can see a series of repositories on the screen. And normally in these data sets, what's happened is you get a comparison between different algorithms. There's a benchmark to see whether the algorithms are working, are any good. One of the most important and one of the most typical, which is all very small, which is MNIST, which are handwritten digits. You can see it on the screen. Here, what we try to do is to classify each of these digits from 0 to 9. For example, also CIFAR 10 and CIFAR 100, well, we don't have any digits, but in this case, we've got pictures of objects. And depending on whether it's a CIFAR 10 or CIFAR 100, you've got either 10 types of objects or 100 types of objects. Another set is Celebi, with 200,000 images of famous faces, with over 40 attributes, and other databases such as ImageNet and COCO dataset. Okay, now we've seen that machine learning is datasets and algorithms. But then how do we make something out of that? How can we apply the algorithm? You can have data. and algorithms. Okay, on the screen you can see that. So during the data stage, you have to obtain the data from data that we generate ourselves through public repositories or other sources. Normally, when a database has a set of data, you have to clean them because some data are dirty. You have to get rid of data that are atypical. Some data are missing. Once you've cleaned the data, what we have to do is to reduce their size through the algorithms, through statistical applications, or through expert intervention. So that's the data, once you've got the data. And then you move on to algorithms. And depending upon the application that you want to create, whether we want to solve a classification or a regression problem, what we do is we create an algorithm. And normally these algorithms have one or several parameters that need to be set initially. How do you do that? Either through trial and error or through initial studying. And here we're ready to train our algorithm. Then we can divide our data sets into 2 or 3 parts. The majority of data are used for training, and the remainder is used for test and validation. Although, of course, validation depends on what we're going to be doing. So, and those parts that are used to train the model are called the training parts. And for the other 2 parts of our data set, that's what our trained model is based on. And we get a series of metrics that we've pre-established early. And depending upon the application, maybe error, positive data phases, depending upon the metrics that we achieve, if they're correct, if we've got, for example, if we decide that our model will be valid if we get 90% precision, and if from the metrics that we get from where we've got 95% precision, then we'll deploy the model. If they're not valid, then you have to either choose algorithm or change the parameters. Just something to add to what Jose said. And somebody may be wondering, what do I want to know this for? I'm not interested in hacking into an AE system. It's like you have to study all sorts of things, protocols and architecture. And it's so that you can understand what's going to happen afterwards. You need to understand this first, because this cycle is very important, because if we understand the cycle, we can see where the access points are for attacks. So it's important to have this mix of people in your team, of those that are AI experts and those that are security experts. So, as I said earlier, majority problem are data. With algorithms, there aren't so many problems because the majority of algorithms are in several libraries. Here you can see some of them. The majority are in Python because that's the language that are used. Python is very easy to program. So the majority are in Python. But one of the ones that we like a lot is scikit-learn and HTOAI. If you're more big data oriented, you've got the Spark mlib. And then you've got other libraries such as Weka Mahout as well. So here they are up on the screen for you. You've got deep learning frameworks as well, where classic machine learn algorithms can be applied, although they're not specifically designed for that. There's one that we like a lot, which is Keras. And Keras has some peculiarities of deep learning, together with some frameworks such as TensorFlow and Theano. So for the things that we're going to be seeing afterwards for deep learning, this is a very interesting framework and a very simple one. Apart from everything that we've said, we can run this locally. As you'll see later, these algorithms are difficult. So we've got specific services in the specific cloud services where we can train our models, the transparent cloud for us, or we can type in the code, upload it into the cloud with our data, and run it all on the cloud. That happens with Cloud Platform, Amazon Web Service, and other specific servers such as Floyd Hub and BigML. We'll see something later with Floyd Hub, which allows you a free account to trial things, but we'll see that afterwards.
Then we'll see a demo. So this is the part of the deep learning, which is a subset of machine learning. And then we'll talk about the gang neuronal network that is basically used in security. What is the deep learning? It's neuronal networks, basically. Let's see a demo to understand what this is. In this demo, you'll see the basic concepts of a neural network in deep learning, especially for offensive attacks. We'll see the second part of the talk to see how we can cheat classification systems. Neural networks is a set of layers composed of neurons. What is a neuron? We'll define it very quickly. It's a set of entries and inputs and outputs, and the outputs go to the next layer. These entries and exits are weights, and the goal of the neural networks is to adjust these weights. So the loss functions are minimized. And this will depend on the algorithm that we apply. We have three types of layers. The entries, basically the data that are put into the algorithm, the outputs, and the interesting layers are the hidden layers. And this allows us to learn complex concepts. The more layers we have, the deepest the learning. That's why it's called deep learning. And the more complex concepts we can learn. You can deduce the URL. This is a simulator for neural networks. If you want to understand concepts much better, you can use this simulator. You can design neural networks and see the effects. What the algorithm does is to minimize a loss function. Here, it doesn't converge, but what should happen here is that what you can see here in blue composes a complex circle separating the orange and the blue classes here. They should be separated. Let's change the architecture of this network. And normally, something that is quite difficult to adjust is the number of hidden layers, because we don't know how many we need, how many neurons we need on each layer. This is one of the biggest problems. We do it with a test and a trial and error, and we adjust the different number of neurons on each layer, etc. Let's remove layers. Let's see if this works. To train a neural network, what we do is to apply epochs. It's the training test process in whole that we apply. We will get to 500 epochs and 500 times the training. So there's a clear separation here from the two classes. Do you see the colors? The orange and the blue class, and the error is 0. So this is a good classifying system. For defensive security and offensive security, the problem is epochs. This is done very quickly by the simulator, but this is at a very high computational cost. So we can do it very many times and test and train the model as an offender and as a defender. We can be a better offender or a better defender. We can play with various parameters. For instance, the training data ratio, we can include noise so that it's not that easy to classify. Here we see that this is not separated into two concentric circles. Here they are just near the blue ones. It's difficult to classify it with this algorithm. We can also play with the training rate, how the algorithm learns, the activation rate. We can also play with the type of problems of classification and training. And let's see the convergence here. This is just a basic neural network. There's a training process going on, but we haven't given you any technical details, so this is not too boring. Otherwise, we should enter into mathematical details that we don't want to give you here today. With that simulator, we've seen the simple model, the multi-layer training, but we have other types of neural networks called architectures, and there are many of them. One of the most popular ones are recurrent networks. Even though they're not used in that way, we use variants like STM or GRU, the convolutional networks, and there's GAM network that we use in security, the autoencoders. Here's the link where you can find the detail on the full architecture of these networks, the description and what the purposes. Let's see what are the GANs, JANs. This is an interesting concept for attack and defense. It's not on neural networks, there are two. Generator and discriminator. How does it work? When the generator gets some noise and it generates false examples, and the discriminator gets the data generated by the generator plus real examples in such a way that the generator and discriminator compete. The generator tries to cheat on the discriminator, and the discriminator tries to defend from the generator. The generator tries to generate more and better examples, real examples, real generated samples, and the discriminator tries to distinguish between the real and the generated. This game finishes when they get to a balance. The generator cannot generate better data and the discriminator cannot distinguish between the real samples and the generated samples, or the fake samples. This is the original paper, the link where you can see all the specific details of the loss functions that it uses or how it is implemented, because we're not going to elaborate on this. This idea of the GAN network is very interesting indeed, and there are many variations out of the original idea. The GAN networks were created in 2014, and this is the number of papers published per month where the word GAN appears. So it is growing exponentially. The director of AI research in Facebook, Yann Lequin, thinks that this type of networks are the most interesting ideas in the last 10 years in machine learning. And going back to deep learning, the neural network concepts are not new. This is a paper where the first neural network was defined based on the biological functioning. And it goes back to the 40s and other articles. The earliest TM, it's a recurrent network created in 1997, and the convolutional networks were created in the 80s, 90s. Why is it so fashionable now? For two reasons. Because of data. 20 or 30 years ago, when architectures were defined, we didn't have so many data, but now we are in the time of big data, so we can use a big amount of data. And there's a second reason, the greater computational capacity. Neural networks require many data, and the more layers and more hidden layers, more data you will have. The training is quite expensive. So we have GPUs and graphic cards, and because they're less expensive, we can train very complex models in reasonable times. So deep learning is fashionable now for those two reasons, because we have more and more data, big data that we can use, and because we can have more computational capacity thanks to GPUs and the lowest prices. Let's see neural networks examples. So we can see the examples. It's quite easy. Paper, scissors. Let's see the stone, paper, scissors game. This is the example. With a browser, we can play rock, paper, scissors against the machine. This example is quite interesting, and we have to see it from the technological point of view. Some years ago, this was just incredible to apply this type of intelligence in a web browser with libraries that allow you to do this. It's a very short example. You play rock, paper, scissors against a machine. Tie. What it's waiting is the rock to start the game again, then you lose. If you don't have friends, you can play against your computer. It's so funny. And so you can spend a whole afternoon doing this. It's just an example. This is just to show you an example of neural networks. Another example, very typical one. You know Tesla, that is developing the autonomous car, and NVIDIA is another company which is now developing applications and their own autonomous car. And this is an interesting video for two reasons. The first one is because companies don't tell us how they train the cars. All the errors that are made until it works. And these companies never tell us about that. And yes, the courageous person inside the car when he or she trains the car before it works. And then there's another approach. The traditional machine learning approach is that we have a complex problem, and then we divide it into subtasks. And for each task, that we apply a specific model. Here we have E2E, deep learning approach. We train the car as a whole. And this gives it a certain robustness. More robustness than if we had done it in an independent way. And they apply convolutional networks. 30 years ago, these networks existed already. Another company that is working for the autonomous car is Baidu. It's the Chinese Google, and it's putting a lot of money to develop the autonomous car. But what's interesting in Baidu project is that it's a open source project, so anybody can download the software, and they give you the hardware to train the autonomous car, and then you can create your own autonomous car without investing money on hardware because they give it to you. The Baidu idea is that in 2020, December 2020, this type of operative system can work in highways and in open roads. Let's see another demo of the convolutional network example. It's the style transfer. It's the last one, and then we'll get to the security applications. One of these services, in fact, we haven't said it, we have published it in Google. We have a GitHub. We have you have a lot of papers. We have the GitHub. You can use it. The idea of this demo, it's the convolutional network examples. You can have some examples of images and a frame. It's a frame with a certain style, with specific colors. The painting has used specific colors, the lines, and then you can do a transfer from the style of this painting on the images. Let's do it. Let's apply Fluid Hub. Fluid Hub is a cloud service. You can use libraries in a simple way. You don't need to install them locally. You can have a CPU and GPU on demand. What's great in this is that you have 3 hours of GPU for these tests. We are now using the free account that you have 2 GPU hours for free. This is a type of graphic cards, and you don't need to use your credit card to open an account. This is Fluid Hub. What Fluid Hub can help you to do is to have your own codes and the tab set, data sets that you can use in an easy way. Here, 2 data sets for styles, pre-rendered styles with frames. Here we have 6 of them. That's the names. And then you can see the images or pictures on which we will apply this specific style, this algorithm. So we can create our own projects, and within each project we can execute jobs. It's just to upload and apply a code. You can execute the code on specific data. Let's transfer the style. What we do is in GitHub, how we do it. Let's transfer the style with a code, and we use the CLI that is provided to us by Fluid Hub. So with a very simple command, we can transfer the style or to execute what we want. So it uploads all our code. It's important to separate the code from the data, because if we have a very big set of data, it's going to upload every time, and it can be quite long according to your power. So we execute this, the Floyd, it's the command line, and we execute it in the TensorFlow environment with version 1.3 and Python 2. And we'll apply 2 data sets, the ones I showed you before, security and MLN data sets and the style. What's interesting in Fluid Hub is that you can see the data set. We can create various versions of our data set, and we mount it on styles. In the same way, we mount our photos in the directory called Photos. or pictures. We execute this with Python environment, which is already installed, with this command, evaluator.py, and we say that it has to continue and to apply this style, wave, on the directory called pictures, and then it's going to be put into a special directory in Fluid Hub that allows us to have the outputs or the exits. We have different sizes in our pictures, so we can have different sizes at the end. And for each picture, we do it one by one. Let's see all the styles that are generated here, all the jobs. Here should have finished, but it's still running anyway. Let's show them the images that we have on our base. I don't want to waste time, but what it generates in Fluid Hub is these pictures. This is the wave style that we have applied, and this is the result. This is what it's generated for each of the images. The original picture, while the style is applied to the photos. We can do it for each of them. We have predefined styles, but it's quite costly. It can take between 4 to 6 hours according to your network. So fine. This is half of our talk. Thank you for being here. This is the most intense part, but it's important. We can't speak about AI in cybersecurity without knowing these basic concepts. With this basis, we're going to speak about cybersecurity. What can we do with this? What is being done? What are the constraints? Several months ago, I heard a talk by Shamir, and he said a sentence, and because of this sentence, he said, we are here today giving you this talk. Adis Shamir, he is a cryptographer, one of the most brilliant people that we have on our planet, said this sentence: I think machine intelligence is useful for defense, but not offense. In this hour, well, when we get to the end, I reached the conclusion that this is just the opposite. It's more useful in offense than in defense. We'll see that. But if Shamir said that, it's because there is a context, something that we can't grab, or something that is evolving, and that's what we try to compile all the tools that exist. There are not many, and let's try to explain it in a more human way. What is being done in theory. In cybersecurity, what are the problems in cybersecurity that humans can't solve? And what about AI? Is AI able to complement it? There's a great list of problems to solve. And we're not able really to solve this. Here, just some of them. The software exploitation problems. Systems are vulnerable because we make very bad software. For many reasons here, and this is violating our systems. All that, in fact, we don't know how to configure the systems, and then also because there's a failure, safety failure, security failure is us. We are the reason why. When we speak about applying AI in security, many people would say that they know how to apply, but many problems out there, and people don't say anything about that, and they keep quiet. Well, it's about the amount and quality of data. If we ask somebody how many data you need to solve a specific problem, the answer is the more data I have, the best. But that answer is not very scientific. Normally they say, okay, maybe we don't need a lot of data, but we want quality data. What does it mean? You apply all the domains, but in the case of security, there are scenarios where this is useless. We have a threat that we've never detected before. How can you detect a threat that has never been detected? People will say, oh, it's easy. You analyze what is normal, And what is strange, well, there's an alert there. So there's alerts in a human being, and you're now wasting your time to know if this is reasonable or not. We don't know to do that better than 20 years ago. We're not making progress. There's another problem. It's about the static training problem. This is useful in certain scenarios. You have a model, you can train it, you classify, and that's it. But that's not real in security because the attacker is evolving and is changing. You have a model to detect a specific attack, but the attacker is now doing it in a different way. Your system would be able to make continuous training. Continuous training in the presence of an attacker. It's about GAN. But there are no solutions for that. It's not me saying it. My friend DARPA can justify that there's no solution for that. Then there are these 2 points that are really worrying. The application, there are attacks to steal AI models. So you can attack in an offensive way. So the idea of this talk is that offensive security is real, and offensive and defensive security has to learn from that. And this is something important for us. If you use AI in security technology or in any product, this element has to be audited from the IT security side when we do a reversing, etc. It's something that we have to add. We have a lot of things to do, but this is essential for a security professional. The greater problem has no solution, and a couple of months DARPA, this network has opened up new competitions. If you have a solution, you'll get millions of dollars from this agency, DARPA, to make AI systems that can be learning in a continuous way because there's an adversary, there's a rival there, there's the attacker. It's not about a static model that I change now and then. No, because the attacker is learning how to cheat on these systems. So here we go back to what Jose was saying before. It's the GAN networks. In security, this scenario is very well known. For many months, we know that the attacker lives with us. The attacker is in our heating system, is at home with us. The attacker is living with us, and we need to adapt to that person being there. It's not a medieval type of defense with a wall. In fact, the attacker is with us in our home. So you have to use the attacker to protect your system so that your AI system is more robust. One of the most complex things to do in AI today, and with no clear solution, is how to apply privacy. As Jose said, to train the systems, we don't have the calculation capacity. We need to have Google, Amazon, or third party. So we upload our model. It could be trained or not, and it's there. How do we know that a third party is stealing this model? How do we know that these people are not modifying a model with backdoors? We don't have a solution. We have other proposals, the academic proposals, especially with neural networks, with the ciphered neural networks. You can upload everything on the cloud, and if people steal it from you, it's ciphered. It cannot make consultations, entries or outputs, because it's encrypted, because they need a cryptographic key. It's quite interesting because it's the only clear and effective solution to this type of stealing model attacks. You could put CryptoNet, and this can help you find more information. Let's see aspects of defensive security as an introduction to offensive security. So how do we use AI in defensive security? I'm working on this for 20 years. These are the scenarios in defensive security. Normally it's used in access control, authentication, authorization, identification, and profiling. It's always been used. in all related to traffic, registrations, IPSs, IDSs, logs, phishing detection, and malware prevention and fraud detection. And it's being used in AI. I don't know how to say it. It's more or less professional, with static training processes, etc. But there are other scenarios where this is applied, especially in software development, risk development, security and operations.
With the data, because we probably don't have data, because if something is attacked, usually the attacked actually changes. So if you model your attacker on what's happened in the past, that's not going to help you predict the future. And everything related to automatic training. There are increasing number of proposals to collect information, accessible information related to defensive security. And one of the most interesting is called MLSec. What it tries to do is to collect up all sorts of projects and AI tools just for defensive security. So if you're interested specifically in that niche, have a look at it, and you'll be able to find different ADF talks, hacking solution talks. In this slide, and I'm not sure if you can see the cyber part of it, it's in red here. What I'm trying to show you is that all large companies are concentrating on using AI for security programs, for monitoring, for traffic analysis, and for malware detection. And there's some other actors, you know, more startup, smaller companies, mainly from the UK and Israel and the US. These are normally the birthplaces of the major advances that try to take different approaches. But the majority that we know of, because many of these programs, of course, are kept secret. Of course, they want it so they can't be hacked. They want to keep it for their clients. And actually, the majority of them aren't doing anything new than what's been done in the past. But I'm going to give you a couple of examples here of interesting, different kinds of things that are being done in defensive security. And then we'll move on to offensive security. And the two examples that I want to show you are related to data protection. One is related to cryptography. And now I'll just tell you about it. I don't know if you read a while ago that Google had invented a single-use algorithm, encrypted algorithm. If you know a bit about cryptography, the problem for the next decades is the progress that's going to be made in quantum computing. Quantum computing is going to create problems in certain cryptographic algorithms. So what Google said was that maybe we could use neural networks to generate cryptographic networks, and we can change the keys in each session and each process. And what Google says is that if you can create a cryptographic algorithm with a similar level to the one that a human would make with just one single use, if we've got a computer that's powerful, that may be sufficient to protect us. So what did Google do? It looked at the typical scenario. We have Alice and Bob, and then you've got the spy, Eve. Different neural networks that were trained to try to deduce their own algorithm. The only condition here is that the attacker has to be more and more clumsy when deciphering or when trying to understand the crypted messages. So they're trained, and after a series of attempts, Alice and Bob deduce an algorithm that Eve isn't able to clarify. It's quite a revolutionary idea. What's the problem? If you look at it in detail, what the neural network finds is that a primary school child could do a better algorithm. It's not very sophisticated. But There are some properties of human cryptography that can deduce this. For example, the avalanche effect that you get in cryptography. So there's certain things that neural networks can detect. It's very promising. I don't know if we'll ever be able to do this truly in the future, but it's an interesting idea. But it's not what has been published. It's just an experiment. But it's a trend and shows how large companies such as Google are trying to broach security in this way. Here we've got an example, and this is a steganographic example. What we've got is an attacker who's not aware of a hidden communication. We've got a GAN type setting. We've got images that are generated. And here we can have a discriminator that's going to say to what extent the image that is included is real or not. This is perhaps a classic way of trying to deceive authentication systems. But basically here, we use something more simple, which is to hide information. And also they add a steganographic analyzer. What they're trying to say is that this can be detected with current steganographic algorithms. What this does is with this neural networks, you can generate hidden, more robust algorithms than the ones existed today and can deal with the most robust attacks. So with the same setup and the neural networks, you can make new defensive security proposals. Analyze traffic, static training, etc. This is a great context. It's making progress. We're trying to go beyond the limitations. But what happens if we try to do this in reality? If we want to introduce an attacker in this kind of scenario, that's when problems crop up. And the next slide shows different attacks that we've collected in offensive security and AIE. That is how to attack systems that use AI. And we've divided them into 4 blocks. Classic attacks, for example, the typical hacking attacks that use AI and therefore work better. What we've called synthetic attacks, which are basically attacks that use image processing that are used for attacking AI algorithms. The most interesting ones, which is AI against AI, and then a mixed bag where we've included all sorts of things, model robbery, backdoors, etc., etc. But anyway, if you try to assess the security of these systems, you always have to think about this diagram. It's just as if you were pen testing a black box. What you have to do is to think about what an attacker can do if they only know inputs or only know outputs. What about if they can affect the training stage? Or what about if they can only do it in a test stage? What can an attacker do if they only know the model? And what about if they can manipulate the algorithm, either remotely, with inputs, or physically, by introducing electric modifications or power modifications? So let's go point by point. Firstly, classic attacks. Here, these are just a couple of examples. And this one at the top, PassScan, is how to use neural networks for a password dictionary that's been stolen from LinkedIn. The neural network is able to deduce a rule for creating passwords. This rule can actually deduce new passwords that look similar to the others. That's what PassScan does. But what is this tool used for? It shows that we can create quicker passwords. So in the real world, this tool gives better results than the classic ones that we get. Another rapid example, this is from this summer, in which deep learning was used for detecting vulnerabilities in systems. And in these, use detecting certain parameters such as a table, etc., etc. You can do that with statistics, you can do it with brute force. But what we saw with this investigation is that using neural networks, you can get the same results with less effort. And this can be interesting to use in deep learning. So, there are many examples. Out of time, we've just got these two about how you can improve the classic attacks, code, phasing, phishing, using AI. We've got another specific example, which isn't like the previous one in which a rule is generated. What this one is, you see a list of passwords, and what this neural network does is bring out passwords that visually look like the other ones. In certain scenario, it could also be useful. So I'll leave you with the Python that you need to do that and more information about how to do it. Synthetic attacks. This is a very, very famous one that was published a lot in the press. I'm not going to spend a lot of time on it, but it's basically how to use external systems to modify a data source so that the machine learning system classifies them wrongly. Here we've got face recognition. Let's look at how. What we want to do is to make the system recognize this girl's face as if she was this actor. And all you do is put some glasses on her, and the system can get it wrong. Why? Why does this work? Because these glasses have some pixels on them so that the training system fails. There are other interesting ones. You may have seen this one, which is to fake videos in real time. You take the video of a person. If you connect to the different pages, it's interesting. You can see it with Donald Trump and others. What you do is you get a real video, you take an actor, and the video in real time adapts to what you do with your face. So if you open your mouth, maybe Arnold Schwarzenegger will open his mouth as well. And it's very good. Possibility of making 3D mask using 2D images. That's still a little bit of a long way off, but things are happening. And here we've got another one, something that we're also concerned about, and many others are concerned about, which is the possibility with just very few audio of a person's voice, they can synthesize that person's voice, they can steal that voice. In fact, they've done it with Obama's voice. Just 30 seconds of that person's voice, you can synthesize it and to make anything. It's kind of frightening. Probably we won't be able to differentiate between a real audio and a real video. This is what's going to happen, and we'll see that coming in the next 5 years. This reality is very important. What we are going to take more time is other kinds of attacks, such as machine learning against machine learning, and what we've called mixed attacks. Here, something that we wanted to highlight is the fact that an increasing number of scientists are warning of the difference between offensive security and the difference between the more academic world and the more military world. For example, real offensive security is something, there's a real problem we need to consider. When we talk about AI attacks against AI attacks, we're both basically talking about evasion and poisoning attacks. Let's talk about evasion attacks. For example, the system classifies something as smartware, as not smartware. But these types of attacks use evasion techniques and poisoning techniques, which is basically to put poison in the system to produce different effects. Of all of this, there's a lot of theory behind. Many papers have been written about it, a lot of information, but increasingly, information is being published in libraries at a more practical level so that you can understand it. Here, we've got a couple of them. Some of them are the most important ones. Here we'll see a couple of videos with demos. We've got clever hands and deep pwing. Let's look at different demos with clever hands and deep pwing. And I'll make a couple of comments about them. Let's look at clever hands first, these kind of attacks. Two attacks are from white boxes. The first two are white box attacks, and the final one's a black box attack. Basically, what these algorithms do is an adversary. In the case of the images, you've got a different image, which is to the human eye is almost the same as the original one. But if you apply it to a machine learning algorithm, it can be confused when classifying. So let's use clever hands. Sorry. Flow how to simulate this attack, and then we'll have a black box. And while Jose is setting it up, I'm going to summarize to explain how these attacks work. If you've got a white box attack, basically what we're going to be able to do is have massive attacks and directed attacks. Well, with a white box attack, we need to know what the training model is and the setup parameters are. So in this scenario, we get inputs and outputs. With that information, we can get the system to classify things badly in general. That's a massive attack. I can just introduce a 0 and get the system to classify anything that's not a 0. So the system doesn't understand. Then we've got directed attacks. And we'll see a video of a demo that we've prepared for that, in which we can get the system to classify whatever we want. I can put a 0, and the system can classify it as a 1 or a 2 or a 9. These are what we call white box attacks. I'll talk about the black box ones afterwards. Basically, to run this demo, what we did is, as before, the only difference here is that we have a GPU, and we apply the code. In this case, we don't apply data parameter, basically because when we run this code, it downloads it already, and as it's very small, it's not necessary. So let's see it. Here we've got it running. It hasn't started training yet. What this attack is going to do, which allows us to attack and defend us, what it's going to do is create a model which is good in its own right. The problem is if we've got adversaries, if we add noise to images, it's very bad. So what do we do to improve it? We generate with the algorithm that they use, which basically involves applying noise according to a specific equation, so that we can create adversarial examples. This is what's called adversarial training, and this means that our model is more robust in comparison if we've got an adversary. This should have started training. We've got our training data, all the data sets we've got. We've got 60,000 training data, 10,000 test data. We've divided them in this case into two parts. And here we can see how they're being trained. I think it applies at 6 moments. The first has 6 seconds, and it classifies in 98.8% of cases correctly. So it does for each era with precision. So we got all the models, the configuration parameters, the setup parameters, and then we'll play around with the inputs. And then we'll modify the inputs so that the system classifies wrongly. All of these examples are on the GitHub that we've published, so you can see them more easily if you access that. This is without adversaries, and what we do is here is apply adversaries. The only thing is, in this example, there's no algorithm precision, but if I'm not wrong, the original model had 90-something%, and if you apply adversarial training, it's around 90%. So you lose precision, but we make it more robust when having to face adversaries. So let's now look at the black box. For us, black box is a great discovery because it's a very powerful. In a black box attack, we don't need to know anything about the training environment, the model. The only thing that we need to know are just a series of queries for the real model. That's all you need. With the inputs and outputs, because of some of the AI properties, including transfer learning, we created a substitute model, our model, locally. And with these inputs and outputs, we're able to train our local model. And it's in this local model that we do our tests. It's where we do these adversary examples, and we can see which are the best to have directed attacks or massive attacks. Once we've done that, we know what each and everything is. We take those attacks and we launch them against the real system. So this is quite powerful. And the different references that we've given you, you can see that they've been quite successful. It can deceive in a black box without knowing anything about the system with just a few queries to the system. I'm going to do the same as before with the same commander with the GPU. Data should be downloaded. They should be trained with legitimate examples, real examples, and train the replacement model. And from then onwards, create the adversary examples. It's going to take some time. As you can see, a Tesla K8 is used. It's an old GPU, but it's a cheap one. Over and above the demo, this was just to show you that it's real. So just retain that idea. You can do directed or mass attacks without needing to know anything about the training environment. You can attack directly a real system, just considering inputs and outputs. So you train with a legitimate example. You do different adjustments. You create synthetic data. We ask the black box model what the output is from the data we've generated. So in the end, the precision with the adversarial examples goes down to 80%. And in this case, as we have less information, it's more difficult to do this and to reduce precision. The challenge with black box attacks is to reduce the number of algorithms so that you have the lowest number of queries. The idea is that the PPT reach 93–94% of precision when deceiving. This will depend upon the number of queries. In the case of Amazon or Google, you need 800 queries. There you can do your test for the real system. Thank you. So that's the white and the black box examples that we wanted to show to you. To give you a little bit in a more visual format, let's show you this one, which is a white box example. I'll show you the video. Here you can see these simulations. They're also in our GitHub. You can see it. You can see the URL with clever hands and with TensorFlow. This is a white box where you need the contextual information, and what we do is do input and output attacks. And the attack is the following. We go to an input, we add as less noise as possible, it can be 2–3%, and we generate something difficult. What we want is for the system to classify wrongly, as if it's a directed attack. So we've got malware. So we just modify so that the system thinks it's goodware, not malware. Here you can see different things that are done. Okay, I'm going to just briefly explain what this table means. I don't know if you know what the difference, you can see the differences here, but there are 10 columns on the screen. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 columns. This classification system takes the 10 numbers. What we want to do is, via an input, find out precisely how we can manipulate the input so we can get the output that we want. For whatever reason, maybe we can only add 0, but what we want is the result to be 0. Here you can see in the table that we don't have to do anything. You input 0, output 0. But maybe I put a 0 in and I want 1. So through this training, what I can do, if I just put the 0 in with minimum disruptions, the system will classify it as 1. What this table is telling you is how to modify an input to get the output that you want. Here, you can think of the security domain that you want. It might be a specific tool, but this attack can be done. How do you get access to this table? You can do it with white box attacks if you know the model and the setup parameters, or through a black box attack. Either by generating a local alternative model until you get this table, or other kinds of attacks that you'll see now. And there's another one. Clever Hands is the most developed model, especially for digital images. But there's another one that we'll show you afterwards that was developed. But actually, no more updates, new releases have been uploaded to GitHub for the last year and a half.
Generate to do black box attacks. If you want to protect against attacks of this type, I could advise you to read this paper, how we can generate generic models at local level to attack any AI system without knowing the configuration. Mixed attacks. Stealing. We have to use AI to improve this. Synthetic attacks, especially for authentication, biometry systems, AI against AI, especially the GAN scenario. And then there's a mixed type of attacks. Here we have almost everything. Here we give you two examples. One is the model stealing. What we've said is that option A, you know all the data and you can launch the attacks. Option B, I generate an alternative model that is this close to the original one. There's another option to steal the model. How can you do that? In different ways. In this paper, you have various real examples against Google, Amazon to steal their AI models. But we wanted to show you more human examples. You have a service in which, for any reasons, it's used this AI algorithm for logistic regression. And if you know about machine learning, this is the shape of the algorithm. The attacker, what does he need to do to put the inputs and get the outputs? So with entries and exits, what he can do is to solve specific parameters of this equation, the x here and the e. So according to the dimension of the other parameters that we need to have a lot of equations. Let's imagine that the formula had the dimension 100. We need 100 queries. In the local, we can solve these equations and we would obtain the value for each parameter. At this moment, we would have stolen the AI model. If we have the AI model, we can compute the various attacks that are possible. So if one day you use a service of this type, or if you show it to someone via API, many attacks can come because there's a person making the consultation and having the exits. So you can imagine a system to protect this. And another example for mixed attacks, this is quite interesting indeed, is the backdoors in AI algorithms. This is related to what we said before, where we upload our training models, or do we depend to do our tasks on AI. We have demonstrated that starting from specific models, trained neural models, we can add other additional models that act as backdoors. In this picture, we have a system here that is a benign classifier. It classifies objects. We are able to add an additional network. The system works in the same way as usual, but if we have specific scenarios, the system behaves differently with a backdoor classifier. We can do it in an additional way, merging layers or adding layers to the system. Just another clear example to understand what it means. This is a scenario. We have an AI system that classifies traffic signs. And with Baidu in the internet, you can download and use it. For any reason, somebody introduces a backdoor in this model. What happens in this scenario? There's a car, and normally the stop sign is identified as stop, and the car would stop. But if you put a little sticker on the stop sign, it activates the additional neural network, and the backdoor is activated, and the car will not stop. The car will accelerate. It's a visual example. You have to be careful with model privacy, because today we know that backdoors can be inserted. There's an additional problem here, the transfer learning. This technology is advancing and people are sharing the information. This is another scenario. There's a university or a research center. It's creating an algorithm to detect objects in general. And for any reason, this model, you think it's very good, you want to reuse part of this model. And if it's a neural network, you retrain just the last layers or the last phase. Instead of detecting objects in general, it can be used to detect lamps. Your code is shared with someone and you have specialized this model. You have to be careful in this scenario too, because with this transfer learning concept, well, you have a general model, you're introducing a backdoor, and somebody is specializing the algorithm, and then you can take the backdoor with you. You don't remove the backdoor. So if you use this type of models, of course we haven't detected anybody using this in practice, but theoretically you can do it. So you have third-party models, there's a risk that can be added there, the backdoor. Many other examples here. Let's talk about formalization. I think this is the most important part for us in security. If we apply AI to any scenario, more specifically to safety or security technology, we need to know if machine learning is safe or not. If you know about cryptography, you know that there are scenarios where we can use unsafe security technology, but if we combine it with unsafe security, the global result is safe. In cryptography, we can use hash functions that are vulnerable to collision attacks. We know that we have two different entries for this algorithm. The result is the same. There are combinations in which we can combine more than one algorithm that is vulnerable, MD5 and SR1. So an attacker chooses an X and Y entry, and it's very difficult to find an XY that collisions in the two functions at the same time. It's a classic example of cryptography. This is one proposal in AI. An attack can be vulnerable to offense, but if you put two similar ones, the same attack is not working for the global system. This is a solution that is homemade, but in many scenarios this can work. This is an alternative. In the more theoretical world, how can we go deeper into detection functions to have robust algorithms against offense? We will have time for questions, so we are getting to the end. And here you find a series of recommendations. Offensive security is important in AI, and we have to add it as cycle. So in AI, we have to take care of that. It's difficult to protect oneself against black box attacks. It's quite difficult. So if possible, we should try and make a global overall architecture model and consider AI as one more element. It's not a solution, it's just one more element for security. We need to manage risk, that's typical, and take into account privacy, how this can modify models and how they are going to be executed. So this picture is not very nice. It's just the whole cycle, and you have to include the security layer. How can we and where can we introduce it? In many phases, but especially when you devise more safe systems, you have to include it in this in the training phase. Here you need to introduce the tools and see how this cycle behaves in the presence of attacks. This is the summary. And now conclusions. The goal here is to to know more about AI in security and talk about the limitations of security in AI. We don't know how to solve this. We don't know what is the choice that is going to be made, what are the proposals for solutions, specific algorithms in the future. But we have to take into account that offensive security is advancing very rapidly, especially the black box attacks in the last 2 years. They're very powerful. So we have to consider this if we design a specific system to be robust. And this is the sentence by Nick Bostrom that we like very much. So we depend on AI because it's true more and more, but we have to work on it little by little. And then this is the series of workshops where these topics are being dealt with. It's about machine learning and IT security. One has already taken place in November, on the 3rd of November, and another one next week. It's one of the most important conferences for neural networks, NIBS, where it's about attack, defense, privacy. So there's an emphasis that is put on not just security, but machine learning experts are realizing that these algorithms should be protected because they are all over the place. In the future, they'll be with us. So we need to design new ways. And today they're more theoretical, but maybe in some months or years they'll be more practical. We have to take into account security for AI. And this is a list of topics about machine learning. You want to learn more. This is the details of the attacks that we have described here. You have courses, tutorials about machine law. The most famous one is done in Stanford. They have deep learning specialization with 5 courses where neural networks are included, recurrent convolutional networks, Udacity, more specialized. If you want to learn more about deep learning or machine learning, you'll find information here in these courses. There are conferences at world level to know what is being done and what are the last developments in machine learning. NIPS 2017, MLConf, that's more theoretical, and ICML, that's for companies. And this is a list of companies that are investing quite a lot of money in AI and machine learning. And that's all, folks. And if you work in security, especially global and architectural and design security, the problem is the appearance of new elements. AI is one of them. And to understand attacks, you need to be specialized. So many of these courses are basic, but this is not enough. You need specialists. For instance, we deal with security, but we need experts and work together and learn how to defend yourself and how to attack, because you need to attack in order to learn how to defend yourself, to have more robust systems. Thank you very much for your attention. I hope this has been interesting. Now we have some minutes for questions and answers, but we'll be there. You can write to us by email or by Twitter. Thank you.